Now let's look into a sample hierarchy or sample interaction of OS component diagram. So I would represent, we have different components like CPU that does on the compute. We would have memory. I hope everybody in this class knows what memory is when we are talking about computers. Then we have different bus. Let me just reinforce a bus with multiple line indicating its speed. So we have CPU and memory over memory bus, which is pretty fast, hence shown by 3 lines. Now we have connection of this further. CPU and memory are connected to a bit slower bus, hence we represented it with 2 lines, which is general IO bus. Also, general IO bus could be something like PCIe bus, if you have heard word PCIe. And over this PCIe bus, different devices like your GPU, NVMe devices, so NVMe SSDs could be connected. And then further down or further outwards, as we just talked about, that storage systems is all about hierarchy. So further away in this hierarchy, we have an even slower bus. That is peripheral IO bus. And our slower storage devices, such as our hard disk, or even our peripheral interaction devices, such as keyboard, mouse, could be connected over this peripheral IO bus. So peripheral IO bus could be SCSI bus, it could be SATA, or it could also be USB, something to which we would plug in our mouse and keyboard, right, with a USB. So this is just a sample diagram that shows interaction of different components, or that specifically shows hierarchy. Now, as we just talked about, why do we have hierarchy? Is thinking of those different axes or thinking of those different properties such as cost, performance, physics, capacity, all this in a contradictory manner. Now, one of you could think or could ask a question or could be wondering in your mind that rather than having these all components in this hierarchy, let's place them all together. Like let's place them all directly to this one bus. Why do we need hierarchy at all, right? We just have a bunch of components. Let's connect all of them together just on a single bus. And wouldn't that solve the problem? Well, that's a place to start with. But now think of the physics or think of the space. How would you accommodate all this component in that space? Imagine that you have a CPU chip that's pretty small, really small. If you have any one of you have opened the um, laptop, or if you have opened the CPU of the desktop, you would have seen the CPU chip on your motherboard. And all these devices now, so if you would have seen an hard disk, a physical hard disk, you know how even the smallest hard disk, how big it is. You would have, maybe you would have had the external hard disk to back up your data, right? So you know what's the usual size of hard disk. Now imagine if you want to keep this hard disk right beside that CPU on the same chip, not just one hard disk, but multiple hard disks. And if you want to keep other devices such as your mouse, keyboard, everything right there, just impractical, right? So then you would have to create some extension bus. With every extension bus, what we are creating is additional latency. So then we would have these multiple devices, such as your memory, GPU, NVMe SSDs, hard disk. All these devices are connected with same speed extension bus. Is that a wise use of components and space? Not much, because this extension bus might not be that fast enough for few devices, and it might be too fast for few devices. So somebody in our ancestors or somebody in olden age came up with a smart idea of hierarchy. Let's keep the things, the devices that are fast near to the compute with a small fast bus. Now I emphasize the word small because if you increase the size of this, in a way you are increasing the space that it occupies in the physical dimension, space dimension, and you are also increasing the latency of operations on this bus because there are many other operations also to be handled. So small is an important word over here. And then let's group the devices in sense like the fastest devices, a bit slower than that, and the slowest devices into different, let's group the devices into these different categories and then have different bus for each one of these group of devices. That's exactly the hierarchy that you're seeing on your screen right now. So CPU is our processing unit. It needs to have data to do something useful. Memory is a really fast device, so it's connected with really fast bus, memory bus. Then we have other additional compute devices such as GPU, as well as additional fast storage devices such as NVMe SSDs. These are connected with a bit slower than memory bus and a bit far from memory bus, but still a very fast bus. That's PCIe bus, general IO bus. And then we have this third category of devices that are big in size. So they wouldn't fit right beside the CPU. It wouldn't make sense to have your CPU and have your keyboard on the same motherboard, right? So thinking of the spatial dimension, temporal dimension, that's the access latency, and thinking of the device processing latency. So what's the speed of the device and the device capacity as well? Because if you have this memory sitting right beside the CPU and this memory is gigantic, when I say gigantic, it's like maybe in some, we have the analogy of megabytes, gigabytes, terabytes, and then zettabytes and so on, petabytes, right? Maybe the version of bytes that we yet are even to name, we don't even know that big, then it wouldn't make sense to have that on the fastest bus as the CPU, because that huge capacity to access that, we are increasing the latency of that device, of this gigantic memory device. So, and in order to have this gigantic memory device, it would need a lot of physical space. So it would be a bigger device. So having like accommodating that bigger device right beside CPU doesn't make sense on the same board. So we have a small but sufficient enough memory device on the motherboard, right, sitting beside it on a very fast bus. Then we have a bit larger versions of devices like NVMe SSDs, but yet smaller than hard disk. Now, in terms of capacity, NVMe SSD could be either larger or same as hard disk, but it's way more faster. So a 1 terabyte of NVMe SSD is definitely faster than 1 terabyte of hard disk. And that's where it's sitting on that general I/O bus, which is faster than peripheral I/O bus. And then you have this really large in capacity. So hard disk can be very, very big, or at least array of hard disks can be very, very big, right? Whole data centers have array of hard disks. And other devices that need not be that fast at working at the access latency of nanoseconds and even smaller than that. But anything that's still fast for humans would be agreeable. Like we are using our mouse, keyboard. We don't think that's slow, right? That's fast enough. The fast enough that our fingers can type, it responses that fast enough. So that's good for us. So those all devices sit on this peripheral bus. Now, for something like this, let's move to a bit more realistic scenario, or bit more. Let me give you an example of one of the real architecture. So next I would share Intel's chipset. Now, for those of you who knows Intel is a big and popular company, you would know that it's one of the most successful product is CPU architecture, and is the chip motherboard architecture, right? Many laptops that we buy has a small sticker and like beside it, Intel inside, that shows that it is using an Intel motherboard inside this laptop. So it did something right for its architecture to be that popular that we are seeing today in most of our computing devices. What is it that Intel did right? Let's look into it's one of the sample chipset. Every Intel chipset is different, and that's the proprietary details or uniqueness of the company, right? So every processor is different by itself, but I'm just giving you a sample of one of it. So it still has the same components, which include CPU, or one of the most critical component. Then it has memory on its memory interconnection. CPU is connected to a graphic processing unit, GPU, over general I/O bus, so something like PCIe. And one of the Intel's proprietary thing, or that made a big difference in the performance of this new architecture, or why Intel chips were as such a success in market, is Intel's proprietary DMI, which stands for direct media interface. Now, over this DMI connects the CPU to I/O chip, and this I/O chip then handles connection to other PCIe non-processing devices, such as it could be network, it could be Optane devices, or it could be any other SSDs. So any device that is storing or that is responsible to store the data and from which we could retrieve the data. But it's not primarily a compute device like GPU. So it has this I/O chip that is responsible to interact with all the I/O devices. So it also has PCIe, then it has other interconnections like eSATA, which connects to RAID. If you are new to this word RAID, hang on, we will discuss it in our upcoming lectures soon. And it also has other devices like USB, and you could have your USB drive. Many of us call it as pen drive or a keychain drive, right? Those connected to this. So this is again one of the Intel's proprietary hierarchy or architecture of storage system components and its layout. What is different in this architecture from this generic architecture? It still have the concept of the generic architecture, keep the faster things near and increase the capacity as you go far. But it has some smart ideas which helped us to do things in a better way. So if you come up with any better, smarter idea, well, you could be the owner of company like Intel for tomorrow, right?